The horizontal stabilizer is mounted on top of the 18-foot-high vertical stabilizer in a T-tail configuration. The horizontal stabilizer has a span of about 40 feet and comprises a center box and a left and right outboard section. In this animation, only the left outboard section is shown. The leading edge of the horizontal stabilizer can be raised or lowered as the entire surface pivots about its hinge points. The stabilizer's normal limit of motion upward is 2.1 degrees. This upward motion tends to pitch the airplane's nose down, abbreviated by the letters A and D. The normal limit of motion downward is 12.2 degrees, which tends to pitch the airplane's nose up, or ANU. Here you see the stabilizer move throughout its full range of motion before returning back to its neutral, or 0-degree position. For the purposes of this presentation, the speed of the stabilizer shown here is twice that of actual operation. The horizontal stabilizer is connected to the vertical stabilizer by hinges at its aft spar and with a single jackscrew actuator assembly at its front spar near its leading edge. The animation will now provide a cutaway view of the tail assembly so that you can view the actuating mechanism for the horizontal stabilizer. As the view shifts, let me take this time to inform you that movement of the stabilizer can be commanded either automatically by the autopilot or manually by the flight crew. Any of these commands activates either the primary or alternate trim motor, shown here in purple. The motors are connected to a gearbox, shown in black, which is needed to rotate the Acme screw, shown in blue, by applying a torque to a titanium torque tube that is held fixed inside the screw. The upper end of the jackscrew assembly is attached to the horizontal stabilizer, and the lower end is threaded through the Acme nut, shown in yellow, which is attached to the vertical stabilizer. The jackscrew assembly also has upper and lower mechanical stops, shown here in green, attached to the screw, to stop screw rotation in case of a malfunction of the normal electrical shutoff controls. The entire jackscrew assembly is covered by a tip fairing on top of the vertical stabilizer. This fairing is attached with brackets that I will mention later in this presentation. As the animation shows the stabilizer moving toward its upper and lower limits of travel, you'll notice that the rotation of the screw through the non-moving nut causes the screw to translate upward and downward. This rotation between the case-hardened steel screw and the softer aluminum bronze nut gradually wears down the thickness of the nut threads. It is important to note here that the Acme nut is, by design, the wearing component in this system. Therefore, frequent lubrication is needed to minimize the rate of nut thread wear in order to maintain the expected wear rate of about 1/1000th of an inch per 1,000 flight hours. Additionally, a periodic inspection procedure to monitor this wear is also required. This inspection is known as the end plate check, and if the wear exceeds 40,000ths of an inch, then the jackscrew assembly is to be replaced. These maintenance and inspection requirements will be discussed in detail later in this meeting. The animation will now depict the system operation and sequence of failures that occurred during the accident flight. Flight data recorder information indicated that the accident airplane's longitudinal trim control system was functioning normally during the airplane's descent and landing into Puerto Vallarta on the flight just before the accident flight. Later, while preparing for takeoff from Puerto Vallarta, the accident flight crew had trimmed the airplane to a 7-degree airplane nose up position, as you see here. As the airplane was climbing out after takeoff, the horizontal stabilizer moved at the normal primary trim motor rate of 1/3 of a degree per second, from 7 degrees to 2 degrees airplane nose up. Thereafter, as the airplane continued to climb through 6,200 feet, the stabilizer moved at the normal alternate trim motor rate of 1/10 of a degree per second, from 2 degrees airplane nose up to 0.4 degrees airplane nose down. Operation of the alternate trim motor during this period is consistent with use of the autopilot. Again, for the purposes of this presentation, the alternate trim motor speed of the stabilizer shown here is twice that of actual operation. As the airplane continued to climb through about 23,000 feet, the stabilizer stopped moving at the 0.4 degree position. This cessation of stabilizer movement is consistent with a mechanical jam. Evidence suggests that this jam occurred due to the deteriorated condition of the Acme nut threads that resulted from a lack of lubrication. 2 hours and 20 minutes after this jam occurred, immediately after the autopilot was disconnected by the flight crew with the activation of the primary trim, the stabilizer traveled from its jammed position to about the 3.1 degree airplane nose down position. Aircraft performance and kinematic analyses indicate that the severely worn threads of the Acme nut stripped out at this point, allowing the Acme screw to be pulled upward through the nut until the lower surface of the Acme nut contacted the lower mechanical stop on the Acme screw. The airplane entered the initial dive as the stabilizer moved. The lower mechanical stop and the torque tube that was connected to it was not designed to withstand the aerodynamic loads produced by the horizontal stabilizer. About 8 minutes later, after the airplane had recovered from the first dive, the torque tube and lower mechanical stops separated. The horizontal stabilizer moved upward from the 3.1 airplane nose down position to about a 3.6 airplane nose down position, where it contacted the fairing brackets that were attached to the structure of the vertical stabilizer. These brackets were never designed to carry the tail loads. Several seconds after the horizontal stabilizer contacted the fairing brackets, the brackets failed, releasing the horizontal stabilizer. The resulting upward movement of the horizontal stabilizer's leading edge caused an uncontrollable downward pitching of the airplane from which recovery was not possible.